Hello dear math students, today we will be covering a very interesting concept, the binomial theorem. By the end of this lesson, you will be able to understand the link between expanding binomials, NCR binomial coefficients, and Pascal's triangle. Finally, we will also take a look at using proof by induction to verify the binomial theorem. Please feel free to hit the like button and subscribe. Enjoy the lesson.
So let's say we had some binomial raised to some power n. How can we find the coefficients or the expansion of this binomial? So let's just experiment with different values of n. If n equals 1, then that's just equal to x plus y. If n equals 2, then that's just equal to x squared plus 2xy plus y squared. If n equals to 3, and it expands to x cubed plus a 3x squared y plus 3y squared x plus y cubed. But what about for higher powers like n equals 6? It becomes very tedious to expand this by hand. So can we find any patterns to make it easier for us? So let's have a look at the coefficients that we get for expanding. If n equals 1, the coefficients we get is 1 and 1. If it's 2, you get the coefficients 1, 2, and 1. If it's 3, you get the coefficients 1, 3, 3, 1. And those numbers are the numbers on Pascal's triangle, where the n is sort of like the row, and the numbers sort of like keep on going. So how can we make sure that these coefficients match? So an alternate form of Pascal's triangle is writing those numbers out in NCR notation. So you start with the number on top, which is sort of like the row number, and the number at the bottom is like how many positions you shift from 0 all the way to the row number. So for example, 2c1, if you follow the NCR formula, where it's n factorial over n minus r factorial times r factorial, where n is the total number of objects, r is the total selections that you have, and c is the total combinations that you could make, then 2c1, it essentially becomes 2 factorial over 1 factorial times 1 factorial, which is 2. So let's use an example of x plus y to the 3. So I'm going to write the terms out, but I won't combine the x's and y's. So you can see how we can arrange these x's and y's out. But they're basically the same because xxx is essentially x cubed. So if you notice, there are 3 different sort of groups of x's and y's where there are 2 x's and 1 y. So I've listed them here. So the amount of combinations you can make with 3 terms is 3 factorial, but the x's here are identical. So it doesn't matter if the first x is first or the second x is first. So in order to compensate, we have to divide 3 factorial by 2 factorial. So you can make 3 factorial over 2 combinations that have the terms with 2 x's and 1 y. So the coefficient of the x squared y term is 3 factorial over 2. And we could also do that with the x times y squared term, which is the same. But with the x cubed and y cubed, there's only one combination of 3 x's and 3 y's. So the coefficient is essentially 3 factorial over 3 factorial. So we can write x plus y to the 3 as in the form of actually NCR notation, where you start from 3c0 all the way to 3c3, which is row 3 of Pascal's triangle. So now that we know that it is the numbers on Pascal's triangle, how can we further use that to come up with a generalization of finding coefficients and prove that?
Alright, so let's try and explore some of the patterns we observe in the expanded form written in NCR notation. So when you take x plus y and raise it to some power n, in this case n equals 3, we can notice that in the first term, x is raised to the power of 3, which is equal to n, and y is raised to the power of 0, and similarly the coefficient r value of NCR starts at 0 as well. But in the last term, everything is flipped, meaning that x is now raised to the power of 0, y is raised to the power of 3, which is also equal to n, and the coefficient r value in NCR is also equal to 3. Hence, we can try to generalize this. So we can see that the x power starts at n, and then at every term it decreases by 1 all the way to 0. And for y, the power starts at 0, increases by 1 every term, all the way to n. And similarly, the NCR coefficient of the R value starts at 0 and also increases all the way to n. But this is just a generalization. So how can we prove that this equation works for every given number? So to do this, we can use a mathematical proof called proof by induction. So ultimately, there are 5 steps to proving by induction. The first step is to write out your statement and define it as Pn, where n is a natural number. Second step is to verify your statement for when n equals the first term, or n equals 1, in which we call the base case. Step number 3 is to assume that your statement is true for n equals some given term in the series. Step number 4 is to prove that your statement is true for n equals to some term plus 1, and you can use your assumption to prove this to be true. And finally, we have to summarize our findings. So it is really easy to visualize this in the example of dominoes. Say I want to assume that by pushing one domino over, it will continuously topple the next domino all the way to an infinite given amount of dominoes. So we need to verify this for the base case, meaning when we push one domino over. So when we push one over and we see that it falls, then we can verify that the base case for when n equals 1 is true. Now we have to assume that the statement is true for when n equals any given term k. So say I want to push the fourth domino over, and if I see that it falls, then we can assume that it is true for when n equals k. Now we can take this a step further and prove that the statement is true for when n equals k plus 1, meaning at any given term k, if I push that domino over, the domino after that, k plus 1, will also fall. And if we can prove this using our assumption, then we can hence assume that by pushing one domino over, the next domino will fall. And this should be true for all n, meaning any given term within the series, and hence by the principle of mathematical induction, we can show that this statement is true. And now we can go back and prove our generalizations that we found earlier about the binomial expansion using mathematical induction.
To prove the binomial theorem using induction, we need to first use a statement, which is the first step. So obviously we aim to prove that P of n is equal to a plus b to the power of n, which is equal to a to the power of n plus n choose 1, etc., as we initially outlined, which is the general formula of the binomial theorem. So for the base case, we first know when n equals to 1, the left-hand side is equal to a plus b, and the right-hand side is similarly equal to a plus b. So thus, left-hand side equals right-hand side, so the base case is successful. Next, for a positive integer k, where k is greater than or equal to 1, assume the statement to be true. So a plus b to the power of k is equal to a to the power of k plus k choose 1, etc., up to b to the power of k. And yeah, this holds true. So for n equals to k plus 1, we have the statement a plus b to the power of n, which is equal to a plus b to the power of k plus 1, is equal to a plus b times a plus b to the power of k. And as we noted above, a plus b to the power of k is just equal to our original statement, so we can expand this to a plus b times the rest. And expanding this out term by term, we get a to the power of k plus 1 plus 1 plus k choose 1 times a to the power of kb, and etc., all the way to the general term where it equals to k choose r plus 1 plus k choose r times a to the power of k minus r plus 1. And Pascal's rule states that if you have n choose r minus 1 and plus n choose r, then this equals to n plus 1 choose r. So using this rule, we can simplify the coefficients of all the terms in the equation above, so that it equals to a to the power of k plus 1 plus k plus 1 choose 1, and then k plus 1 choose r for the general term, all the way up to b to the power of k plus 1. And as k plus 1 equals to n, this is equal to a to the power of n plus etc., which is our original statement. Thus, we can conclude that the result holds true for all natural numbers n. The left-hand side is equal to the right-hand side.